I want to talk through a couple of important ideas, and this is one of the most important things, and this is the reason why we've worked through all this. If you do not already have each of these equations, tables, and graphs, you need to go ahead and get this down on your piece of paper, okay? So pay attention to whether you have the same ideas or not, but the most important part is a couple of conversation pieces that you might need to add some extra details in on, okay? When we look at number 1 up here, we're looking at that relationship between the days that have gone by and the number of pennies that Savannah has, right? So on day 0 there were 5 pennies, day 1 there was 8, 2 there was 11. And we can see that in this graph and in this equation. Now I know that with the equation, thank you Jeffrey, the equation is part of the thing that makes us usually struggle the most. So McKay, can you talk us through how you wrote this explicit equation?
Well, old girl started with 5 pennies, and she added 3 repeatedly.
Okay, so I see the 5, I see the plus 3, so where did that n come from?
That's the multiplying repeatedly.
Okay, well, say that again.
That's the multiplying repeatedly.
Are we multiplying repeatedly?
Adding.
We're adding repeatedly, and mathematically we need to understand how do we show repeated addition? Multiplication, right? So notice she started with 5 pennies, and every day after day 0, we added 3 more. So that's that multiplication right there. Okay? That's what the whole last unit was on, and this is going to give us some more chances to practice this because we need to get better at these skills. And so we see that in the graph here, what shape is there?
Linear.
Linear, right? Now, this isn't fully aligned, and we're going to talk about the difference in a second. There's one thing that I want to modify about this answer for number 1. What am I including?
I forgot the labels.
Labels for the axes. Anytime you are making a graph for a real-world scenario, label your axes. You need to indicate what these numbers are representing. Does anyone have any questions about this table, this equation, or this graph at this point?
Not that one.
Not that one. I know. We'll get to some others in a second. But let's look at the one that Caroline did. Okay? So for this one, we're looking at this number 2, where our family has a small pool for relaxing in the summer that holds 1,500 gallons of water. I decided to fill the pool for the summer. When I had 5 gallons of water in the pool, I decided that I didn't want to stand outside and watch the pool fill. Guys, this is a legitimate thing where you want to pay attention to some ideas like this, because who wants to stand there and wait for a pool to fill 1,500 gallons? Zero desire to do that, right? But you do want to know how long it might take, so they represent this. And we see this in this table. At 0 minutes, there were 5 gallons in the pool. And then we're repeatedly adding how much? 2? Alan, can you tell us where you see that repeated addition by 2 in Caroline's equation? No, in the equation. Jeffrey, do you know where the repeated addition by 2 is coming in Caroline's equation?
Starting with 5.
Well, she is starting with 5. I see that right there. But remember, I'm asking, where's this repeated addition of 2 coming in? Y'all, I'm asking you to look at this equation. Where in this equation do we see repeated addition by 2?
And it's about 2
The
in.
2n? What about the 2n tells you you're repeatedly adding 2?
Because it's 5 plus 2n times or something like that.
Yo, what's happening between the 2 and the n?
It's multiplying.
It's being multiplied.
That's why I got the n up there.
I know. Well, the n isn't to show repeated addition. The n is a what?
Variable.
Variable, right? The n is representing the changing inputs, right? But we multiply by the variable because what is multiplication? Repeated addition. We need to recognize that's where that equation's coming from. Now, remind me if I'm wrong. Can I see this really quickly? Yeah. I want you to look at number 6 on the back. Compare numbers 1 and 2. What similarities do you see?
They're
Both start at 5.
When you say they're both multiplying, what do you mean by that? Like, are they repeatedly multiplying?
I meant they're both like adding. So
Okay, so we see in their tables that they are repeatedly adding, right? We got repeated addition, which in the explicit equation means that there is what operation? Multiplication. So on that number 6, I don't know why we're not already writing this down. This is a detail that we need to notice, that addition, repeated addition in the table, is showing up as multiplication by the variable in the explicit equation.
Oh, no, repeat that again, 'cause I have to write it down. I'm sorry, it's just, I'm
they're both adding.
The repeated addition in the tables shows up in the explicit equation as multiplication by the independent variable. We need to notice those details. That repeated addition is showing up as multiplication in the equation. Now, I want you to look at those graphs again. McKay, you did not connect those points. But Caroline, you did. You're not sure about that, though?
It's because it's a... I don't know.
Do y'all think that Caroline is correct to connect those points and McKay is correct to keep them apart?
Yeah.
Why?
I thought... aren't you supposed to connect them if it's like a... I don't know.
Okay, so let's talk about this.
I don't know.
At any point for Savannah, does she have 7 pennies? No. She goes straight from 5 to
Oh, then I don't know.
8. Okay? At no point does Savannah have 7 pennies. So can I put a point there?
No.
No. This is what we consider or call a discrete model. Right? The idea that the points are isolated. Or not connected. This is the principle of arithmetic and geometric sequences, the idea of a discrete model. However, when I look, and so that's a detail I put under number 6, that it's a discrete model, or number 1 is a discrete model. When I look at number 2, and I look at this pool filling, it started at 5 gallons and it jumps up to 7. Is there any point where the pool has 6 gallons of water?
Yeah.
Oh, yeah.
I mean,
You have to get
does it just magically jump from 5 to 7?
No.
No. Is there a point when it has 6.5 gallons of water? What about 5.5? So you're telling me there's a whole bunch of points in between the points in the table?
Yeah.
And so notice, we can start to fill in all those points, and when I get enough points filled in there, it's creating a what? A line. This is what we mean by a continuous model. Right? There are, does anyone know how many points there are in between the really big points up here?
5.
2. Okay, I don't know.
Infinity.
There you go. It's really weird to think about, but in between just these 2 points, the reason why we make a line there is because there are infinitely many points between any 2 points. Creating a curve. And the reason why I say creating a curve is technically, and there's probably a mathematical detail that you haven't encountered before, but a line is a type of curve. Okay? So we need to know this difference between a discrete model and a continuous model. Whenever there's a continuous, there are infinitely many points between any 2 points, and you identify that by, can I get something in between here? Right? When it's discrete, they're isolated, they're not connected. We good with that detail? Okay? So when I'm looking at the domain for number 1, what would we say the domain for number 1 is? We'll talk more about notation later, but that's just a curly bracket. It would have the number of days of 0, right? Would it ever have half a day? No? So it would jump straight to what? 1 day. And then?
2.
And then?
3.
Notice how I'm having to do those isolated numbers. Those are discrete numbers. But when I look over here and I look at Caroline's, is it just 0, 1, 2, 3, 4? It's everything in between 0 and 4, right? So what we have to do here for this domain is we have to talk about the fact that it's all real numbers. That would be whole numbers. And we use something called interval notation. We'll do more on this later, but it starts at the minute 0, and I don't know how long it takes. We'll just say 4 minutes for now. Have you seen this interval notation before?
Mm-hmm.
Okay, we should have seen it before, so we'll come back to that pretty soon. But what I really want to focus on is numbers 3 and 4 for the last few minutes. You can even see it right here. Is this perfectly linear? Or has it started to curve?
Starting to curve.
Why is it starting to curve there?
Because it has
It's
a multiplicative rate of change.
Has that multiplicative rate of change? We need to pay attention to this. If the money is increasing by 3% every month, what percent do you already start off with?
100.
You always start off with 100%. Right? If you have anything dealing with percentages, you need to recognize you're starting with 100%. Then we're increasing that percentage by 3%, which gives us 103%. And whenever you're dealing with a percentage of, what are you repeatedly doing? Multiplying. I need you to make that note to yourself if you did not already know that. So that is this note here. So that's multiplication, which is why we have this CR, a common ratio of 1.03. We are constantly multiplying by 1.03. Repeatedly, repeatedly, repeatedly. And how do we mathematically show repeated multiplication?
An exponent.
With an exponent. You see how we have an exponent of n right there? See that exponent of n is repeated multiplication? Alright, so notice, should we have connected the points here or should we leave them isolated as a discrete model?
Leave them isolated.
If you look at the context here, I don't know why. You look here at number 3, it explicitly says, if I take my money out before the end of the month, I don't earn the interest, right? So does she get any of the money in between here?
No.
So that would be discrete as well. But we then look at this one with the gallons of water. Is it just going to magically jump from 1,500 down to 1,455?
No.
So it's going to have stuff in between?
Mm-hmm.
So it's going to be continuous. So we need to recognize, again, my domain would just be 0, 1, 2, 3, 4. But this domain would be continuous on all real numbers. If you are not able to get all this information down, 1, I've recorded it so you can go watch it later. But 2, I'd probably take a picture of this to make sure you have all this information down. Have we started to be able to identify the domain of functions? We don't have to know it perfectly, but can we tell when it's going to be these discrete values versus when it's going to be continuous values? That's what I need you to see. Can we tell the difference between arithmetic sequences and linear functions? Discrete is arithmetic, continuous is linear. Geometric is discrete, exponential is continuous. Alright, here is your homework. You need to complete the set section from 2.1 and then fill in the first 3 columns of your vocab for arithmetic means, geometric means, discrete models, and continuous models. Think about what it says at the top of the column and just fill in those first 3 columns.